Hi everyone, welcome to Smart Classroom. This is Mahammood Suhail Mundodan. Welcome to next lecture. Today I am going to introduce you on a new concept, and that is the concept of electric field. I have a charge capital Q at this particular location, and another location I have another charge small q. Take this as my test charge. And there is a separation between the two, which is r, and r is the unit vector from capital Q to small q. Let this force be capital F. Last time we introduced Coulomb's law, that force capital F equal to small q capital Q into Coulomb's constant divided by r square into unit vector r. If the two have the same sign, then the force is in the direction of r. If they have opposite sign, it is in the other direction. Now I introduce the idea of electric field, for which we write the symbol capital E. Electric field EP equal to force divided by test charge small q. Substitute the value of the force small q capital Q into Coulomb constant divided by small q r square into unit vector r. The small q will cancel out. Then finally we will get the electric field at the point P equal to capital Q into Coulomb constant divided by r square into unit vector r. The SI unit of electric field is Newton per Coulomb. If capital Q and small q are positive, then force F is in the direction of unit vector r. Then electric field also in the same direction. If capital Q is negative, then force capital F is towards capital Q. Then electric field also change in the opposite direction. Electric field is the vector, so you can expect arrows. And I have here an example of a charge plus 5. So by convention, the arrows are pointing away from the charge in the same direction that the positive test charge would experience the force. Are you notice that very close to the charge, the arrows are larger than farther away? You see the field vectors, and the direction of the arrow tells you in which direction the force will be if it is a positive test charge. And the length of the vector gives you an idea of the magnitude of the electric field. Very close to the charge, the arrows are larger, and if I move away from the charge, the length is reducing. You see the direction of the field vectors tell you in which direction the force will be if it is a positive test charge. And the length of the vector gives you an idea of the magnitude of the electric field. And here I have another charge -1. It doesn't matter whether it is -1 microcoulomb or -1 nanocoulomb. Just it's a relative representation. And you see now that the electric vectors reverses in direction, pointing towards the minus charge by convention. When you go further out, they are smaller, and you have to go all the way to infinity to the field to become 0, because electric field is fall off by 1 by r square. Next topic, electric field due to system of charge. Let us say here we have Q1, here we have Q2, here we have Q3, and here we have Qi. Now we want to know the electric field at the point P that the test charge experience. Now we can say what is the electric field at P due to Q1 alone. If Q1 is positive, then this might be the representation of E1. If Q2 were negative, this might be the representation of E2, pointing towards the negative charge. And if Q3 were negative, then I would have a contribution of E3, and so on. Now we use the superposition principle as we did last time with Coulomb's law. The net electric field at P, vector EP equal to vector E1 plus vector E2 plus vector E3 plus etc. If you have I charges, it is the sum of the individual E vector of all I charges. That means it is equal to sigma of EI. When we place a small charge Q at the point P, what will be the force on Q at that location P. The electric field vector F equal to small q into vector EP, where EP is the vectorial sum of total electric field vectors at the point P. If Q is positive, then force is in the direction of vector EP. If Q is negative, then force is in the opposite direction of EP. If Q is large, then force will be large. If Q is small, then force will be small. So once you know the electric field, it would be the result of very complicated charge configuration. The real secret behind the concept of electric field is that if you bring any charge at that location and you know what force acts at that point on that charge. If we try to be a little bit quantitative, suppose we have here a charge +5 and a -1. Then we want to know what is the field configuration of these two charges. You can take any point. Electric field is moving away from +5 and moving towards -1. If we very close to -1 put a plus test charge, let's say +Q, very close to -1, then the +Q is attracted towards -1 charge. Now we put the same test charge +Q very far away. What is the net force experienced on +Q? The answer is very far away. The +Q experience a force due to +4 charge. That is the vectorial sum of +5 plus -1 equal to +4. That means very far away the field is like a +4 charge and it's followed by 1/r². Now you see, it's very interesting. Near to -1 the force is towards left, and far away from -1 the force towards right. At a particular point, these two forces cancel out and the force is 0 there. That means the electric field is 0 at this particular point. That's all for today. If you have any query regarding this topic, you can comment me under the comment section. If you like this video, please subscribe and share. To get all our notifications and updates, don't forget to press the bell icon. Thanks for watching. See you next time.